So welcome back to the second session. So we have with us Professor John Hopfield from Princeton University. Of course, Professor Hopfield needs no introduction, but let me take this opportunity to welcome him on behalf of us. So I invite Sita Bro, my fellow colleague, to invite him on behalf of us.
Thanks. So it's an honor and a privilege to be able to introduce Professor John Joseph Hopfield, who has been for a long time been one of my intellectual heroes. He has been a model to many physicists such as myself who work on cross-disciplinary problems, as he began his career as a solid-state physicist, but over a career of nearly 6.5 decades, he has effortlessly crossed boundaries between disciplines as disparate as molecular biology, neuroscience, and combinatorial optimization. John Hopfield was born in Chicago in 1933 to physicist parents and earned his undergraduate degree in physics from Swarthmore College in 1954, and then completed his PhD at Cornell University in 1958, where his advisor was Albert Overhauser. And this year he published a seminal contribution which described the polariton, a quasi-particle resulting from strong coupling of electromagnetic waves with electromagnetic dipole carrying excitations. In the same year, he joined the legendary Bell Labs as a member of the theory group. So this was a time when luminaries such as Claude Shannon, Richard Hamming, and possibly also John Bardeen were working there. Subsequently, he has taught in physics departments of the University of California, Berkeley, and Princeton University. And then he moved to Caltech, where he was instrumental in setting up the computational and neural systems program in 1986, before moving back to Princeton, this time as professor of molecular biology, where he remained till 2008. He continues to be associated with the Princeton Neurosciences Institute. His PhD students over this career have included many who have become very famous scientists in their own right, such as Terry Sejnowski, the computational neuroscientist, Sir David Mackay, who works on information theory, Bernd Halperin, the solid-state physicist, Eric Winfrey, Xiaoping Li, just to name a few. Professor Hoffield's attention was primarily in condensed matter physics till 1974, when, in a major contribution to the field of biology, he demonstrated that the high degree of accuracy present in gene expression can be explained by a mechanism called kinetic proofreading. In 1982, Professor Hopfield went on to propose a model of neural networks to explain how memories are recalled by the brain. This model, often referred to as the Hopfield model, explains how neurons interact to produce stable memories, and further how neuronal systems apply simple processes to complete whole memories based on partial information. This paper and subsequent ones revolutionized the whole field, connecting spin glass theory to neuroscience, allowing a whole generation of physicists to overnight become experts in neuroscience. Daniel Amit, physicist who moved to neuroscience as a result of this paper, has called Professor Hopfield's paper a brilliant step backwards, essentially to point out that the radical simplification which Professor Hopfield made in this paper allowed suddenly a whole set of analytical techniques to be brought to bear in this field, thereby making new advances possible. Professor Hoffield's many awards reflects the interdisciplinary nature of his career, including the Society for Neuroscience Prize in 2012, the Harold Pender Award from the University of Pennsylvania School of Engineering in 2002, Dirac Medal from the International Center for Theoretical Physics in 2001, the International Neural Network Society's Helmholtz Award in 1999, the Benjamin Franklin Medal of 2019, the IEEE Rosenblatt Award of 2009, and most recently the Ludwig Boltzmann Medal. So without further ado, let me invite Professor Hopfield to deliver his talk on something which promises to be very exciting and very relevant for all of us: how to find a problem.
Thank you. I'm very happy to be part of this symposium and to share the today's platform with Professor Dar. Okay, let me begin. My first full-time employment was at the Bell Telephone Laboratories, where the transistor had been invented 10 years earlier. I joined its 6-person theoretical physics group, reporting to work on March 1958. The first half day of employment was spent on administrative detail. I joined a couple of theorists in the cafeteria for lunch and then headed for my new office. Unpacking a few books and journals took an hour. A visit to the 5th floor stockroom produced some lined tablets, pencils, and a held pencil sharpener. I returned to my office and sharpened several pencils.
Professor Hopfield, if I can just interrupt you for a moment. I think the slide is not changing. In case you have changed the slide, we're just still seeing the original title slide.
I should. Yeah, no, I'm
okay,
fine.
Right. Okay, great. Thank you.
That start question has plagued me many times in my research and teaching career. Every scientist, every scholar, every writer, every artist faces this vexing issue of what to work on each day. Most respond by working today to extend a little yesterday's line of thought or line of measurement or plot development or what have you. Most of us, if forced to ask, now what, at a more fundamental level or for a long-term commitment of effort, endeavor to not much change the arena in which we have been happily playing. Most of us spend little time thinking seriously about choosing the research areas we next pursue. You hear very few lectures on how to choose a research direction. Yet, the choice of problems is the primary determinant of what one accomplishes in science. 2 papers that I wrote many years ago form the basis of my recent Boltzmann Award. I will not speak today about the technical issues in these papers. Instead, I'm going to talk on how each of these subjects developed, how the choices were made, and the situations encountered ultimately defined the germ of a useful viewpoint on which mathematics could be overlaid. For shorthand, I refer to this process as the problem choice, but it is not a choice in the sense of choosing one problem from a list of problems. It is really a description of how a useful point of view was winnowed from an analysis of the seemingly random events from one's past history. When viewed with historical hindsight, the development of a problem is generally presented as a logical sequence of correct choices of what to do in a branching decision tree. But without the benefit of hindsight, research is often pursued in random directions, taken with no overwhelming insight, until some idea seems by chance better than others. Only the paths which turn out to be useful are later included in accounts of how science was done. What is physics? To me, growing up with a father and mother of whom both were physicists, physics was not defined by subject matter. The atom, the nucleus, the troposphere, a piece of glass, my bicycle, the phonograph, the washing machine. These were all incidentally the subject matter. Physics was a point of view that the world around us is, with effort, ingenuity, and adequate resources, understandable in a predictive and reasonably quantitative fashion. Being a physicist is the dedication to a quest for this kind of understanding. Of course, neither of my parents ever spoke of what defines physics. It was only much later that I thought about how my upbringing defined a useful worldview. I grew up taking things apart, seeing how they worked, repairing bicycles, exploring chemistry in the kitchen, building flyable model airplanes, crystal sets and simple radios, playing with batteries and coils of wire, and learning to think with my hands and manipulate real objects. Each thing I understood, why my bicycle brakes got hot when they were used, how a crystal set radio worked, how to make a compass, became a self-consistent story which could be incorporated as a small part of a much grander understanding of a complicated system. When author John le Carre was asked who was the model for one of his characters, he often replied in terms of composites of real people he had known. A well-portrayed character needs plausible relations between different aspects of their behavior. It is easy to remember large chunks of several real persons' behavior and to assemble these large chunks into a fictitious person. Self-consistency then arises from what you knew from real life. You don't have to generate it all de novo. Le Carre collected people he met. Similarly, I collected small models of physical understanding. Heedless of the financial consequences of being a physicist, I only briefly considered an alternative career. My high school chemistry teacher had been superb, while my physics teacher lacked an understanding of even the rudiments of mechanics and electricity. Thus influenced, when listing potential majors on college application, I would write physics or chemistry. At Swarthmore College, I was assigned physicist Professor William Elmore as my advisor. We met in his office to discuss my future. He located the student card describing my high school record and the field of study I was considering, took out a pen, and crossed out 2 words. I was remarking, I don't believe we need to consider chemistry. And that is the way my education went. An arbitrary act by Bill Elmore had much more with my being here today in front of you than in anything else. It was not an unreasonable choice, but scarcely a reasoned, logical decision I made. I began looking at graduate schools in physics with an eye to what I might specialize in. My upbringing had particularly focused my interest in physics on the physics of the world around me, not the physics of the nucleus or the cosmos, but rather the physics of the daily world and its technologies. I went to graduate school at Cornell rather than Princeton because in 1954, Cornell had a segment of the department interested in a field then called solid-state physics. In the middle of my second year at Cornell, I approached theoretical physicist Albert W. Overhauser to ask if he would supervise my thesis and help me find a thesis problem. Through courses and doing tripost-like problems, I was rapidly acquiring the tools of theoretical physics, but I had no idea how to find an appropriate research problem. Finding a good problem was never discussed in classes or in seminars. Happily, Overhauser had a list of interesting puzzles. These were often of the form of a paradox. Elementary theoretical analysis of a phenomenon in solid-state physics gives result A. Experiments give entirely different results B. In most of the paradoxes in his list, Overhauser himself had no idea of what was producing the conflict between a common sense theoretical approach and the reality coming from experiments. I picked one having to do with the radiative lifetime of an exciton in a crystal. It became my problem, and Overhauser never worked on it at all. He was enormously supportive as a listener and critic when I went to see him, but finding direction and resolving technical theoretical issues were entirely my problem. The great gift he gave me was the ownership of an interesting question and total responsibility for research and progress. One day he told me that I should start writing up my work, and that was the end of the PhD research. I have done my best to repay my mentor through similarly nurturing another generation of independent students. PhD in hand, I took a position in the theory group at Bell Laboratories. Conyers Herring was the head of the theory group and saw me struggling to identify my next problem to work on. He suggested visiting with experimentalists to get my own sense of where interesting puzzles lay, and I still remember many of those visits. This was the framework within which I met chemist David Thomas and formed a working theory-experiment alliance that ultimately ranged over many different compound semiconductors. It was to provide me with unanticipated problems and paradoxes for 10 years. It provided AT&T with a major knowledge base in compound semiconductors and semiconductor optics, and garnered David and me a joint Oliver Buckley Solid-State Physics Prize. At the time, no one would have guessed that the combination of light and compound semiconductors would have the major technological impact it has enjoyed. However, in 1968, I had run out of problems in condensed matter physics to which my particular talents seemed useful. I went to the Cavendish Laboratory of Cambridge University in the UK on a Guggenheim Fellowship for half a year, hoping to find new, interesting avenues, but found little for me. Returning from Cambridge to Princeton University at my consultancy in the semiconducting group at Bell Labs, I ran into Robert G. Schulman, a chemist at Bell who was doing high-resolution nuclear magnetic resonance experiments on hemoglobin. He told me about the cooperative oxygen binding on the 4 iron atoms in the center of the widely separated heme grooves. An incredible panoply of physics techniques were being used to study the molecule. NMR, EPR, optical spectroscopy, X-ray scattering, X-ray structure studies, neutron scattering, Moss power spectroscopy. All of the very clever experimental techniques to solid-state physics seemed relevant to hemoglobin. Schulman wanted theoretical company to help interpret his NMR results, through which he hoped to understand the physical basis of the physiologically important cooperative oxygen binding. He made a strong effort to interest me in hemoglobin problems and the potential for such studies to move biology toward becoming a hard science. Knowing my talents, biology was a good place for me. Hemoglobin provided me a simple entry from condensed matter physics to biological matter physics. In both fields, the goal was to understand how structure and low-lying excitations were related to measurable and relevant properties. It seemed to me that my background in condensed matter physics might find good use in biology. When Linus Pauling, a double Nobelist in chemistry and in peace, was asked about choosing problems to work on, he remarked, "I ask myself whether the problem I am considering is one to which I am likely to be able to make a contribution." Even Pauling found that a match between a problem and talents was significant. It seemed to me that one singular addition biology brought to the science was the notion of function. There's a small subset of properties that is of great importance to biology, and that evolutionary choices have shaped biological systems so that they function well. The term function is peculiarly biological, occurring in biology and in applied sciences like engineering are pursued for human benefits, but not relevant to pure physics, pure chemistry, astronomy, or geology. Although biology was very complex, if I always focused on function, perhaps I could find within biology some simple physics-like phenomena. The Schulman-Bell Labs group next turned its effort from the protein hemoglobin to the nucleic acid called transfer RNA, tRNA, where they could determine aspects of molecular secondary structure from NMR. Lacking any way to relate such experiments to functional questions, I lost interest in the group's experiments. I did, however, attend many seminars from outside speakers who were describing the functional biological aspects of tRNA without knowing much about its structure. The one that still sticks in my memory 45 years later was Herbert Weisbach on protein synthesis. Filled with far too many details for any physicist to remember, it included a funky movie which it had made of color-coded students playing the role of specific amino acids, RNA, proteins, etc., all wiggling around in the foreground, culminating with a linked chain of amino acid students being generated while phosphate and tRNA students reeled off into oblivion. The only overall impression I remember from it was that there was the extravagant waste of high-energy molecules during protein synthesis. The speaker was intent on describing a linear biochemical pathway for assembling a protein and did not mention energy. Attending this 2-hour talk seemed a complete waste of my time. That same year, I was giving my first biophysics course, designed for physics graduate students at Princeton. I spent an unreasonable amount of time on hemoglobin, which I believed I understood. However, hemoglobin's obvious functional puzzle is about equilibrium, not dynamics. The essence of biology is the dynamics of a driven system, often far from equilibrium. This fact makes hemoglobin a poor introduction to problems of biology. For the last week of class, I made an effort to describe a dynamical problem involving tRNA. That class of molecules was chosen primarily because it was the only biological molecular system, other than hemoglobin, about which I knew anything. tRNA does play a central role in assembling amino acids and proteins, following instructions on messenger RNA. A few minutes of chemist thought led me to conclude that how this is accurately done is in part a problem in chemical dynamics. Undeterred by my ignorance of biochemistry, I turned to the kinetic problem of accurately making proteins for the last week of lectures. Most of the biochemistry research and textbooks describing protein synthesis and Princeton use are based on lock and key descriptions of chemical reactions. Understanding biochemistry was generally viewed as a problem of mapping out what happens. From a physics perspective, most biochemical reactions are possible at room temperature. There will only be different energies associated with similar but different reactions, and thus different Boltzmann factors determining kinetic rates. Discriminations are actually based on energy differences. The biophysicists biochemists A happens and B does not happen should be replaced by things involving finite differences. There's never a zero. Some errors are always made. And you finally get an error fraction, which is determined by the difference in energies of binding of two similar proteins, two similar amino acids that you want to discriminate. I put together a few lectures say, showing that for accurate biosynthesis, a network of chemical reactions should not be pushed to operate too quickly. But the lectures involved only trivial ideas. In the course of the lecture preparation, I made a crude solid-state physics type estimate of the discrimination energy between two very similar amino acids, valine and isoleucine, that differ only in a single methyl group. I calculated roughly 1 in 50 for the maximum ability of any reasonable binding site to discriminate against erroneously using the smaller molecule valine. Unfortunately, the known error rate for that kind of errors was roughly 1 in 3,000. Obviously, my naive physics view of how to calculate binding energy differences just collapsed. As a warning against physicist hubris, I did finally describe my obviously inadequate estimate to the class. 150 versus 1 in 3,000. After the term ended, the issue still nagged me. After a month, I realized there might be a real paradox. My estimate could be roughly right, but loft field could also be correct, and the level of accuracy might not be determined by a simple discrimination energy. At the macroscopic level, a typist can proofread a document and thus produce a final copy in which most of the errors in the original typing have been corrected. One way to explain the accuracy paradox was that the cellular biology contains a way to proofread biochemical reactions at the molecular level, thus obtaining a fraction of errors, which is about 1 in 2,500 from an error rate of an intrinsic error rate of 1 in 50. In short, there might be a fundamental research problem in seeking to understand whether in vivo biochemistry carries out proofreading, and biochemists had simply not noticed because they did not know how to look. I had, years earlier, developed one of my simple understandings of physics to explain Overhauser's most profound discovery, now called the Overhauser effect. This understanding, translated into chemistry instead of spin physics, now hinted that a biochemical relative of the Overhauser effect could attain high accuracy if the biochemical system also involves coupling to an energy source, or accurately, a free energy source. Another way to increase fidelity is merely to weight appropriately. When a chemical complex transiently forms, its probability of continuing to be bound decays exponentially with a lifetime which depends upon its binding energy. Transient complexes of a binding site with its preferred amino acids will have longer lifetimes than those with an incorrect amino acid. To observe this requires knowing that time is passing, thus understanding the difference between the past and the future. This requires irreversibility and thus free energy dissipation. Neither of these two insights describe in detail how any particular biochemical system could proofread. The only common feature of these two viewpoints is that both concepts of how to get better accuracy from a fixed discrimination energy involves coupling the system to an energy source. Remember the 2-hour Weissbach seminar I attended and my physicist's take-home lesson, protein synthesis involved unexplained large amounts of biochemical energy consumption? Now I understood the reason for this free energy loss. I was now certain that proofreading would be obvious when I looked at the biochemical details. Within 2 months, I had found plausible schemes for proofreading and protein synthesis based on known biochemical details, and described experiments that could be critical tests of whether proofreading occurs. For adding an amino acid to a growing protein, a 3-molecule complex was needed. The 3 molecules in the complex were GTP, a molecule tRNA, and an amino acid. The paradigm at the time was that the usage of GTP molecules and the number of amino acids added should therefore be 1-to-1. My prediction was that the stoichiometry was not integer, that there should be slippage, and the stoichiometry somewhat greater than 1, even for the addition of a correct amino acid, and that for adding an incorrect amino acid, the stoichiometric ratio should be much larger, certainly greater than 10-to-1. I gave a talk at Harvard Medical School in 1976, ending with a brief account of proofreading and my prediction about non-stoichiometry in protein synthesis. The first question after my talk was from Robert C. Thompson. He asked, "Would you like to hear the results of such an experiment?" and proceeded to describe his not yet published measurements of stoichiometry ratios that overwhelmingly supported the proofreading idea. It was one of the biggest and most delightful surprises of my career. The 1974 paper was important in my approach to biological problems, for it led me to think about the function of the structure of reaction networks in biology, rather than the function of the structure of the molecules themselves. 6 years later, I was generalizing this view in thinking about networks of neurons rather than the properties of a single neuron. It also led me to think more about problem identification and biophysical research. The unexpected success of the paper was due to its formulation of a new biological problem. It had nothing to do with my knowledge of biochemistry or biology. Pasteur once made a famous remark about chance favoring the prepared mind. I would only comment chance had favored the unprepared but inquiring mind just as well. Now what? I spent the long winter of 1977 at the Bohr Institute in Copenhagen as part of its sporadic but historical outreach toward biology. My task was to run a broad Modern Biology for Physicists seminar series with distinguished speakers from across Europe. I managed to recruit a powerful set of speakers with the help of the Bohr name. In 1932, Niels Bohr had opened the International Congress on Light Therapy with a lecture entitled Light and Life. Bohr asked whether a deep explanation of life itself and the philosophical ambiguities of how to interpret quantum mechanics were intrinsically intertwined. However, in 1977, my distinguished experts in biology emphasized what they understood and skirted around all gaps in their conceptual frameworks and research paradigms. They certainly did not describe biological science as being in need of the help from physicists. I returned to Princeton without a new problem for myself. I was looking for a big problem, not merely a problem. What's the distinction between a big problem and a problem? Let me tell a story. In the early 1970s, I served as the PhD supervisor of a student who next went on to be an experimental postdoc at the laboratory of James D. Watson at Cold Spring Harbor. I saw Jim about 9 months later. Knowing that my student had not yet settled down to work on something particular, I made appropriate apologetic noises. Jim cut me off, remarking, "That's all right. When I first met Francis Crick, he was 35 and he had not yet found a problem." Now, at that point in his career, Crick had actually written 10 publishable papers. But what Watson meant was that Crick was working on minor problems, not a big problem. Whereas what Watson had already grasped and what he was pitching to Crick was the outlines of the big problem that was the essence of all biology, the idea that knowing the structure of DNA would explain the chemical basis for biological heritability. I was now looking for a big problem in biology, for which my unusual background was unique and appropriate preparation. My office telephone rang very shortly before my morning traverse of the Princeton campus from Jadwin Laboratory Physics to Frick Chemistry, where in the fall of 1977, I was giving a course in biophysical chemistry. Expecting a call from a tennis buddy, I had hastily answered the telephone, only to find Francis O. Schmidt on the line. He said that he ran the neuroscience program at MIT, would be transiting Princeton next Wednesday, and would greatly appreciate a half hour, no more, of my time. I had never heard either of Schmidt or the NRP. Needed to head off for lecture. Thought, what's 30 minutes anyway? And agreed to meet with no further contact. The following week, Schmidt descended on me. He described an entity called the Neuroscience Research Program, which chiefly held small meetings in Boston, attended by 20 regular members of the program and 20 visitors. I told him I knew nothing about neuroscience, a word that Schmidt himself had coined some years earlier. He said it didn't matter, just speak on what interests you. So I talked about kinetic proofreading and the general issue of accuracy. The audience, neurologists, neuroendocrinologists, psychologists, electrophysiologists, neuroanatomists, biochemists, understood very little of what I said. It didn't matter. Frank wanted to add a physicist member to the group, hoping to bring someone with diverse science experience to interact with this subject and perhaps help it to become more integrated and a more predictive science. Frank was a believer with a zealous faith that somehow, sometime, science would be able to bridge the gaps between molecules, brains, mind, and matter. I was captivated by the talks at the meeting. How mind emerges from brain is, to me, the deepest question posed by our humanity. Definitely a big problem. It was being pursued in narrow slices as problems by this NRP club of scientists with diverse talents and great enthusiasm. But it appeared to me that the group of scientists would never possibly address the big problem, because the solution can be expressed only in an appropriate mathematical language and structure. None of them involved with the NRP moved easily in this sphere. So I joined the group, hoping to define, construct, or discover something I could usefully do in this field. My basic education in neurobiology came from attending the semi-annual NRP meetings, sitting next to world experts in their fields who would patiently explain to me their interpretation of what was going on. Although Schmidt did try his best to get experts to lecture broadly on their topics and to describe neuroscience in an integrated fashion, he was generally defeated in this enterprise. I had tasked myself to finding an integrated physics view of trying somehow to rise above the disjoint details of the lectures. Brains and machines both compute by evolving their state trajectories. Simple digital computers obtain their answers by starting at an initial state of the machine, implicitly described by a program and some data. They then change state again and again at each tick of the computer clock, according to simple rules built into the hardware chips. Finally, the state change stops, and then the state has been reached where the rules generate no further change. Cellular automata are very special digital computers that had a brief moment in the sun in the late 70s. They involved an array of equivalent cells, like the squares of a checkerboard. Each cell has an internal state that changes in time in a deterministic fashion, according to rules that involve only the internal state of that cell and the internal state of neighboring cells. All cells are equivalent and change their internal state simultaneously. I first heard of cellular automata in reading out Conway's Game of Life in Scientific American, and I surmised that a generalization or a modification of that basic idea might be useful in understanding how a brain operates. I speculated that if the cell state transition rules were made less rigidly structured, more like the network of synapse connections that provide inputs between neurons, and if the synchrony and time were relaxed to reflect neural delays in signal processing, it might be possible to bridge the conceptual chasm between digital computers and neural systems. In the fall of 1978, I began playing with corruptions of the Game of Life to make it slightly more like neurobiology, hoping to see it compute by following the state trajectory to an answer. Unfortunately, I was unable to carry out the mathematics necessary to follow the trajectory of a changing state for any such model. I needed to program a digital computer to simulate such a system and to do computer experiments to gain insight. It is difficult these days to imagine the primitive state of computers in computer laboratories in universities 37 years ago. Machines are slow, machine time is expensive, input to computers was principally through punched cards, and output written by massive printers. TV-type display terminals were rare. I have now available on my desktop roughly 1 million times the computational power I had on my desktop in the late 70s. Given that difference, I made little progress. The basic idea I wanted to pursue was that any computer, whether digital machine or brain, operated by following a dynamical trajectory from a starting point, program and data, to an endpoint, and that trajectory needed stability against perturbations to get the answer reliably, in spite of noise and system imperfections. One young Turk visitor came up to me after I'd given a talk along these lines and said, "Oh, that was Hopfield, that was a beautiful talk. Unfortunately, it has nothing whatsoever to do with neuroscience." Well, times change. In 1978, Caltech appointed a new president, Marvin Goldberger, an eminent theoretical physicist who had chaired Princeton physics. During his honeymoon phase, he talked his faculty into offering me a professorship jointly between chemistry and biology. The quantum chemistry computing facility at Caltech was a splendid environment for trying out models. It supported multi-user real-time computing with video displays, direct keyboard input. My research was a perversion of the intended purpose of this facility, but happily no one was looking. However, it rapidly became apparent that my previous year's speculation on the relationship of brain computation to conventional cellular automata was utterly useless. It is surprisingly difficult to give up on a wrong idea that has been nurtured for a year, rather than being totally abandoned. The cellular automata became perverted into a random, quasi-random neural network. The complex set of logical rules for state transitions was replaced by a rule-inspired biology. After a year more of simulations and mathematics, I gave up on random networks. Instead, I ultimately asked myself, why not try a network with a particular structure chosen to accomplish some simple but profound task that neurobiology does rapidly and that seems natural to biology, but not to ordinary computer hardware? The simplest such task is associative memory. Associative memory is reciprocal. Seeing someone reminds you of their name, or at least did when I was younger, and hearing their name reminds you of what they look like. That fact can be expressed in network structure by making connections that are reciprocal. The mathematics of such networks is closely related to the mathematics of spin systems that are responsible for all the complex forms of magnetism and solids. I knew something of these systems through my connections with theoretical physics. Suddenly, there was a connection between neurobiology and the physics I understood. A big problem at last. A month later, I was writing a paper. Publishing a paper. I had three target audiences: physicists, computer scientists, and neurobiologists. Being a member of the National Academy, I could publish a paper in PNAS at the time without review, but there was an absolute 5-page limit on article length, 3 audiences to address, and too much to say. Concerning the writing of nonfiction, Ernest Hemingway once wrote, "If a writer of prose knows enough about what he is writing about, he may omit things that he knows, and the reader, if the writer is writing truly enough, will have a feeling of those things as strongly as though the writer had stated them." The PNAS limitation forced me to be highly selective in what I said and what was omitted. I had to write science in the style that Hemingway wrote nonfiction. In hindsight, the omission of the almost obvious increased the impact of the paper. The unstated becomes an invitation for others to add to the subject, and thus encouraged a community of contributors to work on such network models. This PNAS paper in 1982 was the first publication in which I used the word neuron. It was to provide an entryway to working in neuroscience for many physicists and computer scientists. Further work connected these networks to many significant applications far beyond associative memory. It is the most cited paper I have ever written. And now what? In the introduction, I remarked that the selection of what to work on is the most important factor in a career of research. I have described the pathways of investigation that led me to 2 problems. In each case, there was a slow personal accumulation of ideas, most often from unrelated chance events, each insignificant, that shaped the way I now viewed science. This accumulation would shape my choice at some fork in the pathways of possibilities to pursue. But I made so many wrong choices. The playwright David Hare wrote, "It's hindsight that makes things look inevitable." Hare said, "I wanted to write a memoir that explained how purely life depends on chance." Hare then went on to describe how he came to write his first play. He was a director with a strong political bent who had never conceived of himself as an author. But when an aspiring author failed to produce a promised script, Hare stepped into the breach and wrote a play, Prof made good, in 4 days in order to have the needed play needed by the troupe of actors he had already hired to rehearse the next week. The unexpected failure of the original author led Hare to becoming a major British playwright. Reading David Hare's account, I felt, that's me. One of my plays was ultimately entitled Kinetic Proofreading, a new mechanism for reducing errors in biosynthetic processes requiring high specificity. A long series of unpredictable events had led me from a childhood exposure to the world as physics to teaching Princeton science courses for which I had far too little background. My need of a lecture topic for the class in which I had insight loomed as acutely as Hare's need of a play for his actors. Previous chance garnering from biology lectures, a few random nuggets of knowledge from condensed matter physics, and I had all that was necessary to begin writing a first draft of this physicist's play. At no point prior to that teaching year had I the slightest notion of such a research direction. My other play was Neural Networks and Physical Systems with Emergent Collective Computational Abilities. Again, knowing so little, I myself could not make a logical, organized effort to construct a big problem. But the bits and pieces that I had understood formed the basis on which I could link together talks from very different specializations to see that they are mathematically related science. A big problem had emerged. What I have done in science relies entirely on experimental and theoretical studies by experts. I have great respect for experts who are willing to attempt communication with someone who is not an expert in their field. I would only add that experts are good at answering questions. To find a new frontier, ask your own questions. Don't worry about how you found them. Thank you. All right. Now,
Thank you so much for that fascinating talk. The floor is now open for questions.
yeah, let's do this.
John, thank you for a fascinating talk. So you started with the question, how mind emerges from brain. Do you understand how mind emerges now?
I understand lots of detail differences, detailed similarities. However, I really do not have any insight into how the larger collective things emerged. I think there have to be multiple layers of emergence, built further on further emergence. And I've been trying to put one step up in a hierarchy, but there's quite a few steps by the time you're down.
So to come to the end of this hierarchy, people sometimes discuss about self-awareness or consciousness. Do you have some insights into that? Can a machine have consciousness, for example?
No, and most of the people you read on consciousness finally get to talking about those different levels of consciousness, awareness, and the bottom level of somebody being anesthetized. Turn the anesthesia up, if they lower the number of things they can do declines. You can see certain functions end as you turn off the anesthesia. But the question of what is at the end of, what is at the top end of the ladder, self-awareness. I have no idea how you define self-awareness. It's almost as though the language of the philosopher and the language of the hard-bitten physicist turned to neurobiology are simply not adequately the same language. And you probably go back to Bohr in 32, feeling that somehow maybe quantum mechanics would give you an escape out of which you could understand how physics and consciousness might be related, although Bohr was not pushing consciousness. But without some kind of real breakthrough of that sort, I have no. I've tried, I failed. I've never written anything on consciousness, and I doubt that I shall. I just don't have the fundamental insight. I think a fundamental insight is needed, and it better go along with some kind of math, or there's not going to be any credibility to it. But I have no idea how to do it. None whatsoever. Quantum computing, who knows?
Thank you very much. No questions. John, I have an additional question. Again, a very controversial issue. You mentioned about Bohr's idea of quantum mechanics, maybe bridging the gap. Recently, there are attempts to say that nuclear spins play some important role in cognition. For example, Matthew Fisher has some idea about Posner molecule and the entanglement of nuclear spins guiding some chemical reactions. What is your impression about those developments?
Well, look, you can take the bird or other animals who part of their homing is by detecting Earth's magnetic field or field gradients. And you can ask whether there are, if you know that magnetism is used, and now you can ask what are the best magnetic detectors you can make out of biochemical parts. And there are some incredible things you can do because the atomic number is so small, singlets, spin singlets and spin triplets, whose electronic spin systems interact with nuclear spins, are certainly a possibility, because you get singlet triplet conversion of exciton-like states by using the coupling between electron spins and statistics on the one hand, the electron spins and nuclear spins on the other. So there are plausible ways of building detectors, at least, using nuclear spins as part of the system at room temperature in biology. That's trying to build devices, and I don't think there's any indication in the electrophysiology lab that anything interesting happens with the spin systems, but not impossible. Not impossible. Two of my friends, Phil Anderson and David Thomas, actually spent a couple rainy Sundays near Bell Labs winding coils of wire to see whether they could actually detect themselves, whether the coils were energized or not, whether they had a measurable magnetic sense. Has Matthew published anything on it?
Sorry, I didn't hear you.
Has Fisher published anything or simply spoken of it?
Oh yeah, Matthew Fisher has a couple of papers on Posner molecule, nuclear spin entanglement, and cognition. Implications on cognition. He says nuclear spin entanglement by long spatial dissociates because of the spin can be really decoupled, can have maintained quantum coherence over second one. So there is a beautiful paper by Matthew Fisher. I can send you the reference.
Yeah. I'd like to see the reference.
Yeah.
I'd like to understand whether this is something which every cell, every synapse can do, or whether you have to build a whole structure in order to observe one such thing.
Right. So here, where the phosphorus nuclear spins decompose and then they carry the information and so on. There are
there's a video. Please do send me the reference.
Thank you very much. And
all right, this seems to have collapsed.
yeah. Okay.
Talk later. Probably time to collapse. Thanks for the opportunity to give this talk. I was very different from the ones that I normally give. But then again, people don't very often talk about how you should talk about it.
Very much.
Okay. Bye all.
Thank you so much, Professor Hopfield. It was a pleasure. So on behalf of the Institute of Mathematical Sciences, let us thank you again for making time for giving this wonderful talk, and we very much look forward to one day inviting you in person at the Institute.
Very good. Thank you very much, and just nice to have a day like this and celebrate
Thank you so much.